We're looking at section 12.2, geometric sequences. So we're going to write geometric sequences, both recursively and with an explicit formula, use them to model situations, and translate between the two forms. As a tree grows, limbs branch off of the trunk, then smaller limbs branch off of these limbs, and each branch splits off into smaller and smaller copies of itself the same way throughout the entire tree. Mathematical object called a fractal tree resembles this growth. So if you notice, we got a vertical line. This is stage 0. And then this is considered the stage 0 and is considered to be one branch. So the length of this branch defines one unit. So stage 1 has 2 branches off of the top of the first branch. So this is stage 1, and then stage 2, and stage 3. For this fractal tree in stage 1, each smaller branch is half of the length of the previous branch. So the smaller branches are each half of the length of the previous branch. This is a 45-degree angle from the direction of the parent branch. So the first 4 iterations, stages 0 through 3, are shown. So if each of the new lengths are half of their previous lengths, the length of the smaller branches here would have a length of 1/4, and the length of the branches here and half again would be 1/8. In stage 2, there are 2 branches drawn on the end of each of the 2 branches drawn in stage 1. So that means there are 4 new branches in stage 2. Each of these branches will be half the length of predecessors, or 1/4 unit in length. So in stage 3, there are 8 new branches in total. In stage 4, you'd have to draw 16 branches. In stage 5, then you'd have to draw 32. Each stage adds twice as many branches as the previous stage. So in stage 0, there was 1 branch, which had a pattern of 1. In stage 1, there were 2 branches. Stage 2, there were 4, 8, 16, 32, 64. So each time we're multiplying 2 times a double, 2 times whatever the previous amount of branches were. And we can write these branches as a power. You'll notice the power is increasing by 1 each time. So the procedure for each stage after stage 0 is to draw 2 branches on each branch added in the previous step. So using the description above, write an equation for the number of new branches in a stage given by the previous stage. So stage S would be NS, and we're going to say stage 3 is N3. So N4 would be 2 times the previous stage, which is N3. N5 would be 2 times the previous stage, N4. N6 would be 2 times the previous stage, N5. So NS would be 2 times the previous stage, and S minus 1, the previous stage. So rewrite the rule for stage S as a function that has a number as an input and the number of new branches. So as we saw in the previous pattern in the table, we could rewrite it as the power 2 to the S. So recall that the domain of the function is the set of all numbers for which the function is defined. N3 is a function of NS is a function of S, and S is the stage number. Since the stage number refers to the number of times the tree has branched, it has to be a whole number. You can't divide a tree a fractional amount of times. So domain of S is all numbers S such that S is a whole number. Our inputs just have to be whole numbers. Similarly, the range of a function is the set of all possible values that the function can output over the domain. So let n of S equal B, and B is the number of new branches. So the range, the number of new branches, 1, 2, 4, 8, 16, 32, so on and so forth. So the range then is all numbers n is equal to 2 to the S, where S again has to be a whole number. So graph the first 5 values of n of S on the axes provided. So at stage 0, there was 1 branch. At stage 1, there were 2 branches. At 2, there were 4 branches. At 3, there were 8 branches. At 4, there were 16 branches. So as s increases, as we move to the right, ns also increases. The values are going up. So that means it's an increasing function. So if we think about the branch length, length is L of s, represented as a function of the stage. So as the stage increased, the lengths decreased as the reciprocal. So it'd be 1 over 2 to the s power. So again, s has to be a whole number. You can't have a fractional stage. So the range would be 1, 1/2, 1/4, 1/8, 1/16, 1/32, so on and so forth. And again, s has to be a whole number. So in stage 3, the lengths of the branches, there were 8 branches, so their each length was 1 over 8, 1 over 16, 1 over 32. So 1 over 2 to the n would be the length there. If we graph these lengths, at stage 0, there is 1 branch, or the length of the branch is 1. At stage 1, the length is 1/2. At stage 2, it's a 1/4. At stage 3, it's an 1/8. Stage 4, it's a 16th. So now as s increases, ls decreases. Our y values are going down, so that makes it a decreasing function. So what is the total of length added at each stage? So if we're thinking about at each stage, the length would be represented by the number of branches added times the length of each added branch. So the number of branches added, we said, was 2 to the s. Their length is 1 over 2 to the s. So each time we're adding a length of 1 to our stage. So then what is the total length of the branches a sequence? Yes, it will be, because stage 1 has a length of 1. If we're then adding 1 as a length each time, the number of branches would increase, or the length would increase by 1 each time until we get to stage s. So writing explicit and recursive rules for geometric sequences. Again, a sequence is a set of numbers related by a common rule. All sequences start with an initial term. This time in a geometric sequence, the ratio of any term to the previous term is constant. So we're taking the terms and making a fraction, a ratio. The constant ratio is called the common ratio, and it's denoted by r. And r cannot be equal to 1. So the explicit form of a sequence, each term is found by evaluating the function f of n is equal to a times r to the n. So a, again, is our initial value. R is that common ratio. Or f of n is equal to a to the r times r to the n minus 1. So note there's 2 forms of the explicit rule because it's permissible to call the initial value the first term or to call AR the first term. So it depends on where we're starting from again. Geometric sequence can also be defined recursively by f of n is equal to r times f to the n minus 1, where f of 0 is a or f of 1 is a, again, depending on the way the terms of the sequence are numbered. F of n is equal to r times f of n minus 1. It's called the recursive rule for the sequence. So we want to write the explicit and recursive rule for the geometric sequence given. So first thing you have to do is determine your initial value and then your common ratio before you can write the rules. So common ratio, you take the change and you make a ratio, a fraction of your function values. So in this case, it's right to left, unusually. So we take 6 over 3, which is 2. So that's your common ratio r. And then your initial value, we can see is 0, 3. So our explicit rule, f of n is equal to our initial value 3 times 2, which is our common ratio, to the n. Our recursive rule then would be f of n is equal to that ratio 2 times f of n minus 1, for n is greater than or equal to 1 and f of 0 equal to 3.